I think that's normal. All right.
Okay.
Thank you.
Great. Thank you for joining my presentation about continuous GFlowNets. This presentation is mainly following a paper that was published in ICML this year, which was joint work with Tristan, Pablo, Jinghuai, Alex, Sasha, Lena, Kolia, and Joshua. I hope I didn't forget anyone. I should have written that. I guess like the first question to ask is, why do we need continuous GFlowNets? And you have probably understood from the previous presentations today that GFlowNets have proven advantages either theoretically or experimentally compared to MCMC, compared to reinforcement learning, and to variational inference. So compared to any of these three domains, like GFlowNets have some advantages. For example, off-policy learning helps GFlowNets more than variational inference. We can sample proportion to rewards rather than maximizing a reward as in reinforcement learning, etc. And also, these proven advantages have been confirmed in many discrete domains, discrete scenarios. For example, in biological sequence design, where the goal is to construct molecules or biological sequences by concatenating small building blocks, such as small molecules or maybe small proteins in general. It has been confirmed in Bayesian structural learning, where the goal is to learn a graph or a DAG that describes the generative process of a given dataset. And here the construction of such a DAG is done sequentially by the addition of edges, directed edges between different nodes. It has been confirmed in the robust scheduling problem, where the goal is to assign a set of operations to different compute nodes or threads, which is known to be an NP-hard problem, and the GFlowNets have been shown to be useful for that. And actually, it's probably still state of the art today. It has been used for discrete image modeling. This is a paper that was published a year or so ago, where and the image you see here is binarized MNIST, where we construct these images of numbers that are binary, so just ones and zeros, given like a set of images. And the way this is trained is with maximum likelihood training that has been presented by Lena in the last talk. And probably many, I mean, not probably, but like surely many other discrete scenarios in which GFlowNets have been proven to be advantageous. So with these 2 points, the fact that there are many advantages and the advantages have been proven in discrete domains, there is the question, I mean, the fact that there are many interesting sampling problems that do not exhibit this discrete like structure. This is what drives us to create a theory for continuous GFlowNets. And these problems that do not exhibit a discrete like structure, I'll cite a few of them. The first one being Bayesian structural learning with parameters. So if we go back like to the Bayesian structural learning in the discrete case, where the goal was just to learn the graph, which is a discrete object because we just need to create edges or like to learn where to put edges between the nodes. Here we also want to learn the parameters, and the parameters are in such a Bayesian DAG, the parent of a node influences its children, and this influence is captured by a function that can be parameterized either as a linear function or by a neural network. And in addition to learning the edges that tell us which are the parents and which are the children, we also need to learn the parameters of these functions. Another interesting problem is learning molecular conformations. So in addition to learning the molecule structure, we also sometimes need to learn the angles between some of the edges, or maybe like the bonds. That's maybe like the more correct term in molecules, given that these angles influence the energy of the molecule. Some molecules with some angles are more stable, are more suited for a given task. And finally, a last task that comes to mind is image generation, well, colored image generation, where we are not limited to only ones and zeros, where we can choose what color we want for every pixel. And obviously, you can think of many other scenarios where the sampling problem does not exhibit the discrete DAG structure. So I believe, like with these 3 points, it's obvious that to ask the question of whether there is an equivalent of GFlowNets in the continuous domains and whether these advantages transfer to the continuous domains. And before answering the question, I will give you a summary of the paper, of what we found while working on this. And the answer is yes. There are a few details to be aware of when training a GFlowNet in a continuous domain. And I'll start by reminding you of the 2 main losses that are used in the discrete settings, so the detailed balance and the trajectory balance. And for the detailed balance, I'm not writing the boundary conditions where we incorporate the reward, but like that's something that should be added to the detailed balance, of course. And I just want you to see that here in the detailed balance and the trajectory balance, the policies we care about are parameterized by their probability mass functions. So the PMF here, it's the probability mass functions. The policy PF S prime given S is a probability mass function condition S. And sometimes we need state flows. So as Kolya mentioned, when we don't use the flow matching conditions, we need extra objects such as the state flow function and the backward policy, which is also a PMF. And for the trajectory balance, but also for the detailed balance, of course, we need the reward function. So for the continuous counterpart, we also have a detailed balance and trajectory balance losses. And the equations look very much like the discrete ones, except that now, for example, for the detailed balance, we do not deal with PMFs, probability mass functions, but we deal with PDFs, the probability density functions. So here, PF S prime is a probability density function of S prime condition S. Same thing, instead of a state flow function, we have a state flow density function, and I'll talk a little bit about the details later. And again, instead of the reward function, we talk about a reward density function. But besides these 3 differences, also, of course, for PB, the equations look pretty much the same. So we can maybe stop the talk here and say that, yeah, of course, you can train a GFlowNet, just use PDFs instead of PMFs, and use the same losses in the log domain to make it more stable. But I'll delve a little bit into the details now. So the first question which is important to answer is, in the discrete domain, the structure is well described by a DAG. We have parents, we have children. We know that in order to go from one state to another, we have to go through this DAG. This DAG captures the structure we want. But in continuous domains, it's a little bit unclear how to talk about or how to generalize the concept of children or how to generalize the concept of parents. It might be a little bit weird to talk about continuum of children or continuum of parents. But still, we need a way to describe something that looks like a DAG structure in a more general space. And so we need some mathematical tools to replace this DAG that we use in the discrete domain. And we need this mathematical tool to satisfy a few desiderata. The first one being, we want to be able to describe a continuum of children and parents, as I mentioned. And we want this continuum to be of arbitrary dimension, meaning that you can have one state that has a unidimensional set of children where, the children lie in a line. or maybe a bidimensional set of children where the children lie in a square or a disk or something like that. And the second thing that we would like is the ability to mix between both continuous and discrete components, because there is no reason to restrict ourselves to the continuous setting only. And one example or corollary of this thing that we want is so we want the child set of a state S. It can be the union, for example, of a continuous subset of the state space, and the exit state, and this exit state that we denote SF sometimes. Basically, if we are able to describe a child set that is this union of continuous and this singleton called SF, this literally means that we can terminate trajectories early. So we do not require the trajectories to have the same length. And just because we want trajectories to not have the same length, we need to be able to describe child sets that include this singleton SF that we'll refer to from now on by the exit or the terminate state. And I'll just show you a few sketches of examples of environments that satisfy these desiderata. Here in the bottom left corner, we consider an environment which is a square. So our points lie within this filled square. It can be anything within this square. And we can consider the starting point to be the bottom left corner. And then we can move anywhere within this quarter disk that is shaded here in gray. So by quarter disk, it means that the set of children of S0, the start state, is a continuous component of the state space, and it is bidimensional because, again, we can move anywhere in the disk and not just the circle. But after this first step, we can constrain the following steps to be within a quarter circle. And I believe that you see it a little bit here, like we have, for example, if you are in this point here, then the next state can lie within this quarter circle here that is centered around the current state. And of course, it has to lie within the square. And so this sketch here shows two trajectories of different lengths. For example, here, after 3 steps, the policy decided to terminate. So it went to the exit state, whereas here it required a few more steps. Another example that we would like to be able to solve with our theory is the one where the number of steps is fixed. We start from an abstract state S0 that does not represent any physical property whatsoever. But then we will make, for example, 100 steps, and at each step, we will sample from a fixed distribution. I mean, not fixed distribution, of course, like we need to learn the parameters of the distribution, but like from a distribution of a fixed family. For example, we can set the family to be Gaussians, and if our space is R2, like the Euclidean space, we can just have, for example, Gaussians with fixed mean and learned variance, or Gaussians with learned mean and fixed variance, or things like that. And after each step, we will sample from a Gaussian until we reach the 100th step. Then we have a state at which we are obliged to terminate. And as a last example, before delving a little bit into the theory, which I promise won't be very mathematical, is the image generation problem, where we start from an empty canvas, that's S0. Then we have to choose which positions, pixels to fill in, and which color to use for those pixels. For example, here, the set of children of S0 is a continuum, because sure, there is a finite number of positions, just 9, but there is an infinite number, or like a continuum of values that each pixel can take. And interestingly, some states can have multiple parents. For example, the state here that has red and blue in these positions have two parents here, because here the forward policy has both a continuous and discrete part. The discrete part is the choice of the location, the pixel, and the continuous part is the choice of the color. But the backward policy only has a discrete component. Here, like if we want to choose what parent S2 has, we just need to remove one pixel. So, and the number of pixels is finite. So this is one typical application of continuous GFlowNets. So I mentioned before that we need a mathematical tool that allows us to describe a continuum of children of arbitrary dimensions, and that allows us to mix between both continuous and discrete parts. And the appropriate mathematical tool we came up with is transition kernels. And very broadly, transition kernels can be seen as a generalization of the concept of measures. I won't go much into the details, and I invite you to read the paper if you want like the mathematical details, but these transistor kernels are basically functions that take as input a state S and a subset of the space, and this subset of the space, we call it B belonging to this set sigma here. And basically it tells you whether the set B is accessible from S. That's what you need to remember from this. So if kappa SB is positive, it just means that part of the set B is accessible from S. It means it contains some of the children of S. If it is 0, it means that B is not accessible from S. And of course, there are a few caveats with open, closed sets, but again, I won't spend much time on it. And going back to the previous examples, where we had the quarter disk and the quarter circle, we can consider these 2 points here. For S0, for example, kappa S0B is 0 if B is outside this quarter disk. And so that means that the support of kappa S0 is the quarter disk. And if you are not at S0, if you are at another point, then the support of kappa S is the quarter disk. For example, if you are at this point, the support is the corresponding quarter circle, not quarter disk. Of course, we have to add to add the singleton SF to mention that we can exit at any point. For the other example, where we start from an abstract state S0 and take a fixed number of steps, our state space is this abstract S0 union. So we have to add a timestamp to our states, which are just normal vectors. So the support of kappa S0 is basically the Euclidean space, but we need the timestamp to be 1. So we need states of the form S1. And if you are at a state ST, then the support is the states of the form ST plus 1. So with this in mind, like with this transistor kernel as the basis of our theory, the generalization of the DAG that we came up with, we called it measurable pointed graph. I promise I will not read this slide, but this is just for reference, and maybe like if you want to ask questions later. But it requires the specification of the state space and these kernels that tell us what are the children and what are the parents of every state. I will, however, mention these 2 last points here, which are 2 important points that you need to be wary of if you want to train a continuous GFlowNet. The first one is you need to make sure that your trajectory lengths are bounded, meaning that you do not want some of your trajectories to have an infinite number of steps. So that's something that you need to enforce in the design of the environment. And of course, there is a mathematical formula for that. And you also need to ensure that all states can be reached from S0, meaning that there is no part of the state space that is unreachable. Again, of course, there is a mathematical formula for that. I will summarize now the key differences and similarities between discrete and continuous GFlowNets. So in the discrete, we talk about the children and parents of a state S, whereas in the generalized GFlowNets, we need to talk about supports of measures, kappa and kappa B. We don't need to spend a lot of time on measures. It's just like the mathematical tool that is required for the theory, but I just want to highlight that there is an equivalence for the notion of children and parents. And instead of the state flow function, we need to talk about a flow measure now, and this measure can have a density U. Instead of the forward policy, we need to talk about a forward kernel that has, of course, a density that we write by small pf. Instead of the backward policy, we have a backward kernel that again has a density. And instead of the reward function, we have a reward measure that has a density. Again, these are just mathematical details, but at the end of the day, we have losses that look exactly like, I mean, at least for reward matching, detailed balance, and trajectory balance, these losses look exactly like their discrete counterparts. And let's just focus for a second on the detailed balance one, where, you know, instead of the state flow function f, we have the state flow density u, so that's us. So theta is just the set of parameters. And instead of the probability mass function pf, we have the probability density function, small pf, and same thing here in the denominator. And of course, we have pretty much the same thing for the trajectory balance loss that is applied to trajectories of length n. We don't need to spend time on flow matching, but there is some small differences with the discrete flow matching, and that's because of the choice that we made in the design of the structured space. But all in all, the training strategy is exactly the same as the one that you have learned for the discrete GFlowNets. You sample your trajectories either according to the current forward policy or kernel, or you can add some noise to it if you want to go off policy, if you want to explore the state space more efficiently. And once you have that trajectory, you either decompose it into transitions if you want to use the detailed balance, or consider the trajectory as a whole if you want to use trajectory balance. You need to evaluate these terms that are inside the loss, and in order to do that, you just need to make a few forward passes in your neural networks, because basically this density U, the flow density U, or the forward kernel density PF, for backward density PB, they're all parameterized by neural networks that take as input a certain state. And once you do these forward passes, you get what's inside the square here, and you can just evaluate the loss, gradient step, update the parameters, repeat until you're satisfied with the results. So that's about it for the theory, and I'll spend the next 5 to 8 minutes talking about a few experimental results we have, and then we'll have some time for questions. So as a validation of this theory, so this is not like a really interesting use case of GFlowNets, but it should be seen as a validation of the theory. We consider a continuous version of the hypergrid toy task. So this hypergrid toy task has been used in many GFlowNet papers, including like the original one by Manuel. So the state space is this square, 0, 1 squared. And the reward function is sparse, that has 4 modes, and the modes are represented by these 4 small squares in yellow. And the transitions follow the example that I showed a few slides ago, that actually I will show again. They follow this rule here. We start from S0, we need to move within the quarter circle of a given radius that we call rho, for the first step, and after the first step, we can either terminate or move within the quarter circle, again, of the fixed radius. So now I'll go back to the other slide. But basically, once you have this strategy that describes our measurable point of the graph. Basically, it tells us what are the children, what are the parents of every state. So this design, basically, it makes the environment satisfy the constraints that we had before. So all the equations, especially the last two ones that I said, that trajectory length needs to be bounded and all states reachable by S0. So this is satisfied, and you can convince yourself with it, I suppose, pretty easily. In the second image, so this one here, we see samples from a GFlowNet trained with trajectory balance. Actually, it's not really samples. So we train a GFlowNet, we get samples from that, and then we fit a kernel density estimator, and we get this nice contour plot. And the choice of the policy we made is that's why we have circles or disks instead of squares. It was like hard to, I mean, we can probably prove that it's impossible to reach square densities like this, like with step function, with the choice of densities we made. So there is an important caveat of continuous GFlowNets that I would like to highlight here. So in discrete GFlowNets, and this is actually for the next three figures that I will explain. So for the discrete GFlowNets, the policies, whether it's forward or backward, they are parameterized with logits. So the neural networks that take as input a state S, they output logits that represent a categorical distribution because we have a finite set of children and we just need logits for that. But with continuous GFlowNets, we have an extra degree of freedom because we need to choose the family of distributions we want. For example, we can choose our policy to be Gaussian, and for that we need our neural network to output the mean and the variances, or maybe just the mean, as a function of the current state. Here for this example, we chose a mixture of beta distributions. And why it's beta distributions? So beta distributions are continuous distributions over compact domains. So it's bounded as opposed to Gaussians, which are unbounded. So that's why we chose betas. And we chose it to be like a mixture of betas in order to describe a richer family of distributions. So if you use this mixture of beta distributions, we need to output the mixture parameters that, like the parameters that tell you, I guess you know what mixture of distribution is. I don't need to explain that. And we need to output the concentration parameters of the betas. So this poses something to be, it leads to something to be extra careful about. Basically, we need to make sure that the family of distributions we are dealing with can satisfy the detailed balance or the trajectory balance conditions. Because if we choose like a poor family, maybe we can never reach a zero loss, because as in like the detailed balance or trajectory balance can never be satisfied. So this is what the next three figures show. So the first one, so this one here, what does it show? We consider a uniform backward policy. So by that, I mean that every state has a continuum of parents that belong to a quarter circle that is in the bottom left of that state. So of course, the radius rho. So we start with this backward policy, and we start with samples from the reward distribution. Like we directly sample from the true reward, like because it's a toy task, we have access to the true reward. And with these samples, we take backward steps using the backward policy until we reach S1. S1 meaning the state that comes right after S0. So that's why we get a landscape or a support that is within this quarter disk. So this is rho, that is the radius. And basically, we bring back the samples to S1 and we fit a kernel density estimator and we get this distribution here. So this is the distribution that this is what the forward policy at S0 should lead to. And, like there is a huge mass here on the left edge, on the bottom edge, there is some mass here in the middle, and it's pretty hard to match that on one step using a mixture of betas. Whereas if we consider a learned backward policy, then if we do the same process of starting with samples from the reward and bringing them back to S1, then we get this nice plot here where the mass is more regular, and it is easier to match that with a forward policy that is a mixture of betas. And this is represented by the fifth figure here. And what this means, basically, is that whether it's detailed balance or trajectory balance, these conditions are satisfied better if the backward policy is learned. Meaning, by satisfied better, it means that the loss reaches something that is closer to zero. And this is again shown by the learning curves here in the bottom. Maybe you can just focus on trajectory balance in blue for radius equals to 0.25, where we see that if we fix PB to be uniform, then we plateau to something that's around 3 times 10 to the minus 3. Whereas if we learn PB as well, then we are allowing PF to match this learned PB more easily. So the detailed balance or the trajectory balance condition is satisfied more easily, and we are able to reach a lower value for the loss. And of course, this is also apparent in detailed balance and also apparent if we change the radius. I'll stop talking about this example now. I guess I spent more time than expected, but I'll be happy to ask questions, to answer questions about it later on. And I'll quickly talk about this task of learning molecular conformations. So we are given a certain molecule where the atoms are fixed, but we have 2 degrees of freedom, which are these 2 angles, psi and phi, phi. And basically, these 2 angles, they influence the energy of the molecule. So the molecule is more stable given some configuration of these 2 angles. So one particularity of this task, and this is why I'm talking about it, is that the state space has an interesting topology, because these angles, basically, let's call they live within the 0 to pi, and 2 pi is the same thing as 0 in if we talk about angles. So if we talk about just one angle, we're talking about a circle, because 2 pi is the same thing as 0. And if you talk about 2 angles, we talk about a circle that is horizontal and a circle that is vertical to that, and we are given a torus, and torus, something that looks like a donut. So our state space is a torus. It's not the normal Euclidean space, and you can think of it this way. Basically, this space that is represented by a square, you should wrap it, like WRAP in your head, where the right edge is the same thing as the left edge, and the top edge is the same thing as the bottom edge. So this is a projection of a torus in the square. So this left figure here, we have the energy landscape from which the reward density is derived. This is the true energy landscape that tells you for a given value of psi and phi, what is the corresponding energy. And here in the right figure, this is the energy landscape that is obtained by fitting kernel density estimator on samples from a trained GFlowNet. And we can see that we can match the true energy landscape pretty accurately. But again, like the point of this slide is just to mention that we are able to solve tasks that have an interesting topology that is not just Euclidean. And finally, as a last experiment, I'd like to mention this one about posteriors over graphs and parameters. So it's Bayesian structural learning with parameters that I mentioned in the first slide. I'll show it again actually before going to the details. It's the task here where the goal is to start from an empty graph that represents the nodes, and then the goal is to add the edges sequentially, and once we are satisfied with the structure, then we have to learn the parameters that are associated to each one of those edges. And long story short is that we compared GFlowNets to before comparing. What this task is you are given a data set of, let's say, 3 variables. So it's just a set of points in 3 dimensions. And the goal is to construct the graph between 3 variables that tell you, which are the parents, which are basically the graph that generated this data. And we did this with 3, 4, or 5 variables. And back then, and I guess still now, back then, the state-of-the-art algorithms were BCDNets and DIPs. They took this data set and they output a posterior over graphs. And the numbers that you see here are basically the Jensen-Shannon divergence between the learned posterior and the true posterior. And long story short, like the lower it is, the better. And what we found is that with the GFlowNets, we get significant improvements. So we can surely say that GFlowNets are currently state-of-the-art algorithms. I don't know if something has come since then. This is like February 2023, but it's either state-of-the-art or almost state-of-the-art today. So this concludes my talk. I just want to shamelessly advertise this Torch GFN library that now supports continuous environments, and Joseph will probably talk a little bit about that in the next presentation. And, these are the references that I used, either the papers or the figures that I copied. And thank you for your attention, and I'd be happy to hear your questions now.
Anyone with questions is welcome to come up to the microphones.
Yeah, thank you for the nice talk. Now, I have a question about which policies we should use in practice. So in my understanding, in diffusion models, people, for example, for images, people use Gaussian policies. And for molecular conformation, I think people use graph neural networks or something. But I'm curious, in GFlowNets case, let's say I want to sample from just EXP, reward function, which policies we should use in practice, depending on domains.
So you said EXP, sample from EXP? I'm not sure I understand this part of the question.
If the goal is just to sample from exponential, reward function, let's say the goal is standard goal in GFlowNets, and the domain is continuous, image or molecular conformation, which policies do you recommend to use in practice?
I don't think there is a generic answer to that. It really depends on the task at hand. But if your domain is unbounded, then I would say that the natural choice is to use a Gaussian, for which you need to learn the mean and variance. But if your domain is bounded, then you need to consider other distributions, such as the one I mentioned before, like beta or mixture of betas. But I suppose that, I don't have an example on the top of my head right now, but there might be many other settings where the distribution you should consider is more tailored to the task at hand. And one last point is, I'll go back to this slide here where I mentioned that the choice of the family of distributions is really important, because if you make the wrong choice, then maybe your detailed balance or director balance conditions can never be satisfied. So yeah, you need to be careful about the choice of distributions.
Thank you. For the molecular conformation, which policies did you use?
So this one, it followed the. Let me go back to this slide. It followed this example here where there was a fixed number of steps. So it's called stochastic control with GFlowNets, where we start with these abstract states and then we do 100 steps. And actually, I forgot which distribution you used. Maybe like Collier, I remember. I think it's Gaussian.
If I'm not mistaken, because it's a distribution for each dimension, you have a distribution over the circle. I think what was used is a mixture of von Mises distributions, or maybe circular Gaussians. Alex actually maybe can answer this better.
Yeah, I remember
in
that.
the room. Yeah, it was 10 steps in the paper and a mixture of 5 components, 5 von Mises distributions. But yeah, the details are in the paper.
Thank you very much.
Thank you for your question.
Are there any other questions? No? Okay, thank you very much, Salem. We'll resume.